metals, bricks, and mats. With more time, gotta continuously scan this. So once we earliest spot, when we talk is the spot detector takes not useful. Kind of hard. So what they did is basically created a chip that had given area, and we take a temperature at each point in that area. That's essentially what it is image use. But the next is temperatures. Looks, it's almost so the amplitude of fixed radiation is correlated to the area of the or this pixel to this pixel. Now there are some yeah, then we're looking. So there's some key performance parameters. The first is the thermal sensitivity, and all these. So thermal sensitivity is how much of a temperature difference can be reliable. For the cameras we have, for instance, the FLIR 1 Pros, those are about $400. It can actually skip any 2 points. Can divide each Clear One Pro, not quite. Okay, the third one, temperatures at the effect. And the oftentimes they have in Fahrenheit was like but the way the chip is based is it's a bunch of whole grid of temperatures. That is image resolution. It does not mean it's not the number of pixels screens on lower resolution. And how many points temperature? Time you pull the trigger, it's recording temperatures. So more sense. sensor, right? Or we it's not the same. So what that we can calculate, pick up. Photo lens, focus. But from far away you can't. So take all that into account when we're figuring out, look at, or now, once you have what object I got a couple exercises to do this. So this this is the top view of our You have one where they're not. So in order to do the calculation, the first thing we do is half. We have to get a, we're going to use trigonometry. We have to have that right angle triangle. I'm hearing mumbles and moans. Trigonometry. Trigonometry. Yay. SOHCAHTOA. That. SOHCAHTOA. Sine. Opposite over hypotenuse. Cosine. Adjacent over hypotenuse. Tangent. Opposite over adjacent. I won't do what my teacher did when I was learning this. It was wildly inappropriate. Think Native American and SOHCAHTOA. But she wasn't quite so politically correct about it. She was fun. Interesting. So anyways, looking at halfway, we make a right triangle. So we're trying to figure out how our smallest discontinuity. Basically, what is 3 pixels wide, right? So 3 by 3 square is the minimum area we need to have. So how many is that? So half of this, so half the pixels is 232 pixels wide. It's still 10 feet away, but our angle now, the theta angle is only 12 degrees instead of 24, because we're only. So how do we set this up? Use trigonometry. And in this case, it's set up for tangent. We don't know the hypotenuse. We're trying to find opposite. We have adjacent. We know the angle. So the tangent of 12 equals opposite. So we're trying to find over adjacent, 10. Remember, this is going to be in feet. 10 equals 2.13 feet. Okay? So over 2.13 feet, we have 232 pixels. 232 pixels. Right? This. So what's the width of a single pixel? We take our distance, we divide by the number of pixels, 232, and 0.00918 feet. At that point, we might as well convert to inches. How do you convert feet to inches? Multiply by 12. So each pixel is roughly 0.1102, roughly a tenth of an inch wide. Okay. At 10 feet away, I've got each pixel is roughly 1/10 of an inch wide. Here, this 2. Bring that up here. So the minimum 9 square pixels is 3 by 3. So the smallest discontinuity that I can image is 1/3 of an inch, 0.33 inches. Anything smaller than that, what do I have to do? Move closer. Right? So if my minimum, my flaw size that fails the part is 0.25 inches, what do I have to do? If I have to find something that's 0.25 inches or larger, what would I have to do? If I was 10 feet away, the smallest was 0.333. So if I had to find something that was a 1/4 inch, anything up to a 1/4 inch is okay, but if it's a 1/4 inch or bigger, it's not. What do I have to do? Move closer. What about if I could have flaws up to an inch? What would I probably want to do? You could take a step back. Why would I want to move further away? You can take fewer pictures. You can image a larger area all at once if you need to. Maybe you got the whole object in your view already. Okay, great. But that's where understanding your camera, knowing how many pixels you have, what the ratios are, what the angles are, and what your aspect ratios are. That's where it becomes important in here to be able to say, if I have to find a flaw, and that flaw is a certain size, where do I have to stand? How close do I have to be? Because you're setting your distance from you to the object. That's something you cannot change after you've taken the picture. Okay, you can try to zoom in on your computer, it's bigger, you're not actually covering. So in this scenario, you can expect an accurate image for a discontinuity that is a minimum of 0.33 inches. And again, because we have the same field of view, there's square pixels, it'll apply for both the horizontal and vertical planes. If you were to do this same calculation with the Clear One, small camera, those are rectangular pixels. You would need to look at both the vertical and the horizontal to figure out which one is more restrictive. Okay. When we take it, the quality of your image directly affects its ability to provide accurate information. If you take a bad image, you're not going to be able to do anything after the fact to fix it. Okay. You can change. So when we start talking about parameters are the ideas about it. I've talked about emissivity. I can go in and I can change what the emissivity, what our emissivity baseline value is. That just goes into the algorithm, temp calculation. I can tell the camera before or after what the temperature is in the room. I can tell it before or after what the humidity is. But there are three things that I cannot fix after the fact. This is where that forward acronym, the lab comes into play. So focus, blurry images can't be used. No way to fix it. Okay. So your image must be in focus. Range, make sure you use the proper temperature range on the camera. Must be able to detect in the expected range. Correct range on multi-range cameras. Both our cameras are multi-range. The E95's got 3 ranges. The Clear One Pro is a dual range. And then distance, that's the working distance. That's what the calculations we just did had to deal with. How far is the lens from the object, and will we get enough pixel coverage to find the flaws defined? And you can't just zoom in on an image to fix distance. It just won't happen. So forward, focus, range, and distance. If those are good, every other thing we can adjust on the camera can also be adjusted. It can be adjusted on the camera after you take the picture. It can be adjusted in analysis software after you download it to a computer or a tablet. But you can fix 3 items after the fact. So in the camera, these are the ones that can be adjusted either before or in what's called post-processing. The most important is 0 to 1. And the reference we use for the electrical tape that I pulled out and showed you, the industry standard is called Super 30. Or you can do Super, I think it's Super 88 is like the thicker, heavy. They're the same surface, they both have something of 0.95. So that's what we can use for our standard in order to figure out the emissivity of basically any material surface in the world. We then need to find out, you actually don't find these in order, but this is the order of importance. We typically find the reflected temperature first using a diffuse reflector. So a thermal camera, diffuse reflector, this is the tinfoil panel. Take a picture of it, get the average temp coming in. The idea behind that is the assumption is just about everything you see on that panel is reflected because tinfoil, aluminum foil is a really, really good reflector of infrared. So most of what it's sending back is reflected rather than emitted. So whatever you measure there, you can say, yep, that's the general heat or infrared energy bouncing around the room, bouncing around the space, bouncing around the area. These are, number one, kind of medium. So emissivity is absolute number one. You got to get that right. Collected temperature, that's kind of a middle of the pack second, okay, in terms of importance. Everything below it, relative humidity, atmospheric temperature, object distance, especially if the distances we're working, is way, way, way down the distance, fourth and fifth. It's going to have, especially if the near distances we're working, 2 feet to 20 feet, it really doesn't have a big impact, but you still want to take it into account. So relative humidity, I estimated because we don't have a hygrometer. If you take outside humidity, and it's warmer indoors, it's probably going to be lower. In the summer, if the air conditioning is running, it's definitely going to be lower indoors. Air conditioning removes moisture from the air. But if you're outside, if we have the doors open to the outside, you can pretty much say, yep, look on your weather. Or if you were to know for sure, you would get a calibrated hygrometer. Atmospheric temperature, hit her with a thermometer. I've got some, I got to get some batteries from the battery stuff. Mike ordered me some new batteries, but we'll get some batteries. Just some little temp meters, temp and wind speed meters. And then object distance. And the reason the object distance is so important is because it itself doesn't make much of a difference. What it's doing is it's telling the camera the further away you are, the more humidity and atmospheric temperature come into play. Because it's that air between the camera lens and the object, that has the humidity in it, that has the heat in it. How is that going to change the infrared signal as it gets from the object to the lens? So you can see where if you're fairly close, you're not looking through a lot of air. If you're really far away, then these become more disturbed. So again, in our case, we're mainly in fairly temperature controlled environments. Humidity here, though it gets humid in the summer, this time of year, it's nothing ridiculous. It's probably in the 50 to 70% range on a given day right now. And we're fairly close to our object. We're between 0 and 20 feet. It's rare you'll be imaging anything. So that's why I said emissivity is number one, temperature is number two, relative humidity, temperature, object distance. Those are 3, 4, 5. They're kind of a collective third, but it's kind of like this is the Olympic sprinter, right? This maybe is high school track star, right? This is like me trying to run a sprint. Okay. I'm not a fast runner if you didn't catch that. Even if I didn't have an extra 50 pounds, I wouldn't be a fast runner, or was a fast runner. I played line in high school. I hit people. I could run into people. I did not run with the ball. I also cannot catch a football worth of legs. So we've acquired our image. Now we're going to analyze it and a few more details on analysis. So what we're going to mainly do is direct viewing, and this is mainly discontinuities, and by larger, anything that small discontinuities, stuff where you're getting down to like the 1/10 of an inch or third. If you're talking about something that's less than about a 1/4 inch, that's small discontinuities. Unless you're really close. You have our panel you're going to be looking at. It's about yay big, a couple feet by about a foot. It's got hexagonal honeycomb in it, so honeycomb panel. You can image the honeycomb pattern. Okay, and they're about 1/4 inch diameter honeycombs. You can see that just fine with the naked eye. Plus, you're only imaging it from a few feet away. So you could go back and run those same calculations from 2 or 3 feet rather than 10. Things need to have fairly strong diffusivity contrast. Okay, if you have a piece of metal and a piece of metal, they're going to have very little contrast in how they pretty much dissipates through. But if you've got 2 different types of composites or different thicker versus thinner screws, you're going to get different. Big one, looking for trapped water. It does have its limitations, though. It's not as sensitive to low aspect ratio are those ones that are deeper than they are wide. We're looking for more, this is better for finding wide rather than deep. Okay. Go out there, something hits the side of a composite airplane, it causes delamination. It's not going to put a chunk through, it's going to kind of pop off, right? And so the part of mineral diffusion is the heat diffuses. You'll kind of see the size of what you're looking at change. Remember, it's going to appear bigger than what it actually is. It is based on element. How well can you see? How well can you tune your image to be able to pick up details or certain indications? Surface temperature variations can lead to false positives. The group I showed today, I didn't see this on Tuesday, but the group that was in lab today, I was holding on to the composite panel before I imaged it with the camera, and you could actually see where I'd been holding on to. Perceptibly, there wasn't changes. It just helped. Must view excitation response sequence. So you want to take several images over time. Heat your part up, take images as it cools back down. Cool your part, take images as it warms back up. You may have to look at it at different points in time in order to see that moving through and make a determination of what's going on. And then be careful that emitted radiation is what you're looking at rather than reflected radiation. Okay. So make sure you don't have a lot of heat. Even something that doesn't reflect a lot of heat, it's still going to have some reflection. Thing's a perfect one for emissivity. So, if you have warm objects nearby, that can throw it off. You're imaging something right here, and you got your cup of coffee sitting next to it. That can reflect off that surface. So try to put it in as clean of a room as possible, space, right? Overhead lights. Even though like these LED lights in here, they will give off a heat signature. Not as much as a fluorescent light or an incandescent bulb. Like the fluorescent lights we have in the lab, you can see those reflections all over the place. These ones you'd still be able to pick up a reflection, probably on the tabletops, or any kind of surface. The process analysis, you have to have special software that is able to run algorithms where what it does, it basically looks at pixel by pixel and compares what it sees to the neighboring pixels. And there's all kinds of different algorithms, like how this looks around, what it's. But the advantages are better repeatability. You get a computer doing these. These are used a lot in industrial production. They mount a thermal camera, the image gets fed into an algorithm. That algorithm automatically decides whether the process is working like it should. The place where I went to learn how to do this, it was hosted at a facility that basically takes thermal cameras and integrates them into production lines where they seal plastic packaging. And as soon as the plastic packaging is sealed, a thermal image is taken of it, and a computer basically looks at that thermal image and says, yes, it was properly sealed, or no, there's a cold spot here, so it didn't melt the plastic, it wouldn't have melted the plastic together, or got too hot where it could have melted through rather than bonding two pieces together. That was all done by computers. It could do it on an assembly line where stuff was flying. Just like a blur of stuff going. It's just taking picture. It's analyzing everyone. Pretty cool. It can be higher sensitivity. You'll see, right? We look at these pictures that have color, right? Do you think there's much of it? If you've got two pixels next to each other that are 0.03 degrees Celsius different, do you think there's going to be much of a color difference on the picture we look at? Not unless you shrink your color range down really. So computers, though, they can pick out, they're like, yeah, that one's 0.00, that one's 1.003, that one's 1.006, that one's 1.009, that one's 1.000, that one's 1.08. There's one oddball in the middle here, what's going on, right? A computer can pick that up, so it's more. So typically they're a personal computer, laptop coupled with the thermal camera. They make units now for aerospace. Opco is one company that makes it. Simple to complex algorithms that can analyze pixels over time, over distance, all kinds of stuff. And they can detect very, very small spectral discontinuities. They can define, they can kind of get rid of that haloing effect and define exactly where the damage is, okay, versus where it's just diffusion taking place. And they can find discontinuities with very, very little contrast in diffusivity. And here's the big one. It takes bias out of the equation. It does not presume that there will be or will not be something to find, right? The computer just looks at the data, crunches the numbers. So it removes your bias. Oh, I've scanned this thing 1,000 times. I've never found it. That's typically what NDT is. Most of the time you look at something, you're not going to find it. The lab, again, samples I've got do have things to find. But hopefully when you're out in the field, you're not finding stuff every time. If you're finding stuff every time you do NDT, there's something wrong with the process. Something's failing. And then you're going to go into your reliability, supportability, maintainability, RMS, right? You're going to try to figure out how do we stop this from being found every time. That doesn't mean you stop doing the inspection. It means you fix the problem. Okay. So an example of signal processing. So the first, this is a 5-ply graphic epoxy laminate of aluminum honeycombs. You got aluminum honeycomb structure with graphite on top and bottom, carbon fiber top and bottom. So these are taken, images taken, this is a flash method here. So this is where they do a quick flash of light, that's your excitation, and then pictures are taken right after. So you're talking about very, very minute changes in object temperature. So 0.3 seconds, 0.6 seconds, 1.28 seconds after the flash. So single flash, a bunch of pictures all within a second and a half. So if you look at the raw images, not a lot of difference, right? Even where there is difference, it kind of fades pretty quick. You can see it. Right? But if they run what's called thermographic signal reconstruction, fancy algorithm for trying to increase contrast, you can see a lot more come into view along the bottom, right? Where you can see all kinds of different simulated flaws or simulated features in that bottom right picture there, 1.28 seconds after they've run that, where you wouldn't see that if you were just looking at it qualitatively with your eyes. So that's where it's important to perform. There's another one. Your eyes, see the blue one. You perform, in this case, signal processing. This is algorithmic signal processing. You spread out the temperature differences rather than keeping them linear. Your highest temperatures, you push up significantly. Your lowest temperatures, you push down significantly. You spread it logarithmically between. And now you can begin to see differences in the diffusivity of the material caused by impact center there. That's it. You have a couple videos I can play as you're heading out.